Okay, so I just noticed that my notes weren't all that thorough for class 7. So I am going to put together some examples and lecture material for this one. All right, so, well, I guess this was a hint I gave for um, homework 3 previously. So you can kind of see what my quick return looks like. In this case, it's a quick kick. And then here's another one. This is for the bucket dump. So in case you want to see that ahead of the time of being posted. All right, so for statics review, remember we're usually dealing with 2D problems. We could create static problems that are 3D, but in terms of our review, these are going to be fine. And the magic of the statics is for Newton's the first and third laws. That they need to balance out. So an object in motion tends to stay in motion unless acted upon by an outside force, or the net forces are equal, and moments are equal to 0. In the third laws, we have equal and opposite reactions. So the magic is from the free body diagram, the FBD, and it's the cornerstone, I believe, of all solid mechanics related engineering. We need to draw the FBD properly, and the magic word, remember, is on. What do I mean by that? We always think about the forces that are acting onto the free body diagram. So all the arrows are pointing in the direction that the outside world is affecting the FBD. It can often be difficult if you didn't have this mindset, if you weren't thinking this onward, to get yourself backwards in your forces. But so that's the brilliance of the FBD, and it's in its simplicity, is that if we follow this concept of and thought process of forces acting onto a body, we can get their proper direction and there in that context, and then be able to work through them and apply the X and Y direction and the moments. Right, so we can do this, like I said, in 3D, but for our purposes, we're going to stick with 2D. And let's talk about some things that we want to consider. These are all excerpts from Beer Johnson's, I guess he used the 9th edition. I think they're up to the 12th edition at this point. So this is an important thing, that we don't draw the ground when it's an FBD, because it's got the F in there. It's free, so it can't touch Mother Earth. Right, so you see in this image right here, this is just the image on the left. On here, there is no ground. We have to remove the ground away. That could just be symbolically to help us, make sure that we're following this procedure. But it is an important concept, right? So all external forces should be indicated on the free body diagram. These forces represent the actions exerted on, there's that here, the free body diagram, by the ground and by the bodies which have been detached. Another thing to consider in the free body diagram is forces can't be seen. They're internal. It's an internal thing happening, and so we must do the F. We must free the thing apart so we can expose those forces. The weight of the body is considered, so the acceleration of gravity is considered a force, and it's acting at the center of mass of the piece, which for lots of things they might be like homogeneous and the constant thickness, so it ends up also being at the centroid of the thing. It has to be the center of mass. And then the magnitudes and directions of the known external forces should be clearly marked onto the diagram. All right, so you might want to be putting an angle onto there, or in this case, we have a 3, 4, 5. Little notations. The more important things of anything is the labeling the forces and the reactions. I tend to prefer for reactions to use R for everything. So that's what I would call this, and I would call this an RY. But quite often they'll use the letter, capital letter, for the reactions and placing onto there. There's also a naming system. Quite often will be like if you had two separate parts, you might write the force as being D acting on E. In this case, they just decided that because we had this thing right here, that we would call that part DE, and so this is force DE. Um, Books and authors tend to have different methods of notating the thing. I think consistency is probably the most important thing. Um, I personally like the R's for reactions and then the F for forces placed onto it. Um, so let's see. Okay, let's see. Other things I want to mention as part of this that's in these notes. You can read this. You don't have to read it on the video. I have posted the PDF of this. Um, so yeah, reactions are the things that happen from I usually consider that to be the ground or the supports. I calling those reactions, and then there's other pieces are external forces acting on there. You could probably make an argument for them all being reactions in some respects, but generally speaking, for the main part to be concerned with, um, I use reactions to be like where it's attached to the ground. So here are some basic reactions at the supports and connections. Some of them might be obvious to you, some of them not so much. So when you have like a roller of this sort right here, or even a rocker, because we're not going in a large motion, so it's totally fine that the only reaction is right there. But of course, when I draw an arrow on top of that, I'm actually kind of breaking some rules because you can't see that arrow. You can only see the arrow when the ground is replaced and they have friction. So here's really, you can think of this as a degree of freedom type of thing, right? This is constrained 1 degree of freedom right here, and its reaction. So you look for things. These are often things to look for, like a cable. It can only experience tension and only in the line of its action, which is kind of an obvious, but it's a good thing to note. All right, here's what we've already we're actually introducing something that's important, but it still counts. The short link doesn't matter how long the link is; it only has 2 points on it. So we can prove this in a moment that that's considered a two-force member. So I'm entering. This is one of the things to look for: a two-force member. And a two-force member has the trait that it can only have forces that are in line with it. Now it could be in compression or it could be tension, but the forces have to be in line with each other. We could prove that. But that's a good thing to be on the lookout for. It also counts with these reactions. An interesting one where we have a sliding piece where there's no friction. If there's no friction, there can't be any forces in that direction. It can only be forces perpendicular to the sliding action right there. Interesting, I know. And you might start thinking that there's some contradictory thing here, but we can work all those out when we write the thing out. For a pinned portion right here or on a rough surface, we generally will have a force that has both X and Y components. We generally break them apart, right? And as I said, I usually have the labeled as R's within the X and the Y. And then a fixed support, and this would be probably your most commonly, we would have like a cantilevered beam, something like this right here, where we have a force in it. When we do a free body diagram on it, we will have a supporting force. So this is the force down onto the thing. Supporting force, which I'll call Ry. There's nothing in the X direction, but to balance this out, we must do the sum of the moments. And if this force is going about this point right here, causing a clockwise direction, then we must have a moment right here. I've taken to start going R as a subscript for the moment, and then another letter. In this case, we might call it about Z, if this was X and Y, because the moment would be about the Z-axis. I might even include another letter to indicate where I was talking about, but it seems like a lot of subscripts. So I think these are just the same thing except larger because I was worried about too much work on there, too much being too small when projecting in class. So you'll notice this two force member, and there's a section that's talking about them. If the joints can't experience any about a moment, right there, your conclusion has to be like if you had like a bar like this right here, and you were to take this sum of the moments about this spot right there, and it can't sustain a moment, then it can't have a force in that direction because there's no way that would balance out. It can only have a force in either that direction or in this direction. So there's your two force member. There's a lot of words to that you can read, but I decided, I guess, when I made this, that was important that I included these words inside there. The two force member you can kind of prove to yourself. Here's a weird one that you might not recall. I know that I probably didn't. In fact, I know I didn't. When you have a three force member, you're going to find some point about which they intersect. Boom. I don't know how useful or how many times that actually comes up all that often. It's not nearly as much as the two force member, but it does. It is a true thing. So this is a section, and I've already made my this video 11 minutes long, so I might go into the next section. Let me see how many more slides I have. Boom, 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 boom. No, I'm going to keep on going. Okay, so remember when you have so this we'll call this a simple mechanism, right? The way to approach this is to break it down into parts. I will say for some things, it might make sense to make multiple FBDs, some with a collection of parts. I can try to show you what I mean by way of example, probably the best way. But here we can take a look, and we could maybe start with the little wire or whatever this thing is a little whatever we're trying to cut or crush right here, and isolate this thing. They've decided to go Q and Q. I don't agree with that not negative sign or this negative sign being located there. While it is true, one is positive, one is negative, or one is the opposite of the other, just the arrow is indicating its direction, so you don't need to put negatives in there. But that's what they're doing with the explanation right in there. So first off, this makes sense. This thing is trying to crush that. Now, because we're going to separate the thing out, we could then say, well, we must have these forces equal and opposite to what these forces were, right? So that's what this narrative is talking about, equal and opposite. But this is probably the thing that we'll want to do to try to figure these things out. And we want to usually we'll take the sum of the moments about this spot right there to be able to, so if we know the crushing that's happening here, how much it crushed, we could find out how much the P is here by taking the sum of the moments about the spot. And likewise, the same thing down with this other part. So we're often taking something apart. So here's a nutcracker type of here. I guess that looks sort of like a nut, I guess. So we have this piece, and we're going to assume that this thing is on the ground, I guess. Right, so this is attached to something. But we want to separate things out and see the moments. Now, one of the first, we'll see the moments. We're going to see the forces. So one of the very first things that should jump into our heads is right there, this link. AC is a two-force member. That will determine the forces at A and the force at C. It doesn't have any choice. It has to be along this line of action. That's the mindset we want to take in. So we break it apart, and we could see, sure enough, and even from observation, we could see that it's likely that this is in compression as we're pushing through. We could also, when we get to this piece right here, we can see that it's going. If we're taking the sum of the moments about B right here, this F23 has to be going in this direction. And by the way, the subscripts for this thing, and I think this makes sense, is to say that this is part 2. So this is a force on 2 by 3. Right? So sometimes I've seen books that actually do it the other way. It's like it'll be this is part 3 acting on 2. But if you just want to keep a system going to keep things and recognize that F32 is the equal to magnitude to F23, but they're in opposite directions. So the trick here is to break this thing into components. I'll go red. This component, so we go this F23Y and this F23X, right? And then so take the sum of the moments about B, set it equal to 0, counterclockwise is positive. So you end up saying, and I'll use the number here. So it's going to be 5 times, looks like 8 inches, right? That 5 and that 3, right? But now we're going to go clockwise. So we have minus F23 X times 1.5. And then you have also F2. So we're going to go also minus F23Y, and that's going to be times 3 is equal to 0. But we know that F23X is equal to F23 times the cosine of that angle. They didn't give us the angle, so we can't actually do the thing. And then we have F23Y is F23, oh, writing faster, I'm thinking, sine. Okay, so plugging those into here, right into there, and right into there. We only have one unknown, that's F23, so we're able to find F23. That's the basic idea of trying, and then we start walking through the other parts, right? So we're able to, let's say that we have F23, boom. Now we can place them over here and place them over here. We know that F32 is going to be equal to F34. And then we could go, oh, now we're going to know that F is right into here. And this one we're not going to do the sum of the moments. We'll just balance out. So if we were trying to figure out how much force is on the nut right here, we would say that it was going to be sum of the forces in the y direction equals 0. And we would have F nut minus F43, which again is the same magnitude as F23, times the sine of that theta equals 0. So now we're able to find how much force is being placed on the nut because of the 5 pounds. That's the big idea. 18 minutes. I think we have examples. This is an example, almost the exact same thing as this one, except we're using numbers. I'll see if I have a video for that already. If not, I'll do that one. And maybe this one in the same video. I don't know. I think we have a video on mechanical advantage. I'll look at it. I'll look for that. So I'll see you soon.